Oi, todo mundo. Boa tarde a todos. Bom, hoje retomamos os seminários do GDOP, né, o segundo semestre. E hoje temos presencialmente aqui com a gente a doutora Maria Mastropietro. Atualmente ela é pós-doc com o professor Valério Carruba, Itália, e doutorado em pequenos corpos do sistema solar no Institut für Geophysik und Extraterrestrische Physik, Alemanha. Ela vai falar para a gente hoje sobre Main Belt Comets and Disrupted Asteroids, Distinguish Sublimation from Disruption. Então, obrigada e fique à vontade.
Hello, and thank you, everyone. I'm currently working on LSST data, asteroids, rotational periods, colors, taxonomies, but today I want to talk about my PhD thesis, which focused on active asteroids, in particular two main belt comets, 324P La Sagra and 2010 LH15, and one disrupted asteroid, 62412. So I will explain the differences between main belt comets and disrupted asteroids. Active asteroids are objects that are located in the main belt comet, in the main asteroid belt, sorry. And they exhibit cometary activity, tail, dust emission, coma, while having asteroids orbit. They are divided into main belt comets, which show activity due to sublimation of volatiles, and disrupted asteroids, which show activity due to rotation. In this plot, we see the eccentricity and semi-major axis distribution of different objects in the solar system. Here in gray, there are the asteroids in the main belt, located in a low eccentricity region. Then in blue, comets, and purple, near. And in the main belt, we see in green main belt comets, including LH15 and 324P. LH15 is in the middle main belt, and 324P in the outer main belt. Then in red, disrupted asteroids, including 62412, located in the outer main belt. And in yellow, active asteroids, which we do not know the activity. So, as I said, the dust emission for this object can be due to sublimation of volatiles. In the main belt comets have subsurface ice covered by a dusty layer, and so when they reach perihelion, sublimation happens, and we have dust emission, gas emission if the ice is exposed. And this exposure of ice can happen with impacts. So with an impact, if the ice is exposed, we have sublimation, but we also have dust emission in general. And dust emission can also happen with rotational instability. So for example, if an asteroid's spin rate increases due to YORP, then the asteroid reaches a critical limit for which we have mass loss from the surface, and so this can lead to dust emission or breakup. When main belt comets were first discovered in 1996, it was surprising to have that water ice presence there, because water ice is unstable against sublimation at the surface temperatures of asteroids in the main belt. However, according to numerical simulations, water ice can survive on gigayear timescales under a protective dusty layer. And so the presence of water in this object can help us study the thermal and compositional history of the solar system, and to place constraint on protosolar disk models. So when we observe an active asteroid and we observe the dust emission, is it due to is it proof of presence of water, or is it just dust emission produced mechanically? And this is not always straightforward. In this scheme, we see an asteroid with the ice buried beneath a protective dusty layer. If there is an impact or if there is rotational instability, when the ice is exposed, we see sublimation, and so ejection of dust and gas. And this activity is recurrent at near perihelion and for different perihelia. However, if the ice is not exposed, then we only see dust emission. And this is what we see for disrupted asteroids. This is what we see for main belt comets. In these cases, if a small portion of the ice is exposed, then we can see a sublimation event, but it is only a one-time event, not recurrent, like for main belt comets. So for main belt comets, we see recurrent activity at near perihelion, and it can occur for different perihelia. The dust emission can last weeks or months, and this is what we see for 324P and LH15. For disrupted asteroids instead, like 62412, we see only a one-time event that is usually episodic, and it is not recurrent. 324P at perihelia in 2010, 15, and 21. It was observed, it showed activity at all these three perihelia. So this recurrent activity means sublimation activity, and that's why it's a main belt comet. For LH15, the situation is similar. It had activity, it had perihelia in 2010, 15, 19, and 24. It showed activity in 2010 and 19 observed. And so this recurrent activity also means sublimation. That's why it's a main belt comet. For 62412 instead, this situation is a bit different. It had perihelia in 2013, 18, and 24. It showed dust emission only in 2014, and since it is a fast rotator, probably this was the cause of the activity. Now let's look at the evolution of the activity for this object in details. For 324P, I analyzed different images when it was both active and inactive. When it was inactive in 2013, we can see just a point source. In the other cases, instead, we see a tail or coma when it was active. So I analyzed different images for over a period of around 11 years. And this is just a part of the images I analyzed. And by doing photometry on all those images, and by plotting the absolute magnitude over true anomaly, we can see a decrease of the activity over time. The three different colors corresponds to the three different perihelion passages: green in 2010, blue in 2015, and red in 2021. So we see a decrease of the activity, and this is probably due to depletion of volatiles, or it can also be due to mantling. To explain mantling, the idea is that when ice is exposed, dust and particles are ejected due to sublimation, but some particles can stay or fall back onto the surface. So they create a new protective dusty layer. At the next perihelion passage, the less ice is exposed, or the thermal energy needed to penetrate this layer of the dust is thicker, and so the sublimation strength is weaker. We can also see a particular feature that is very common for main belt comets. The activity doesn't occur exactly at perihelion, but after perihelion, and this is due to the time needed for the thermal wave to penetrate the surface and reach the subsurface ice. And then we see around through an anomaly of 120 degrees that the activity stabilized around a constant value, in this case for 3 to 4p, 18.4 magnitude. And this is when the activity has ceased and the object is inactive. For LH15, we see its activity only in archival images, in these 3 images on the top. In 2010 and 19, we see a tail in all these images. And since it was a newly discovered main belt comet, we wanted to characterize its nucleus. And so we observed it when it was inactive to not have contamination of tail and coma, to have more information on its physical properties. For 62412, this is the dust emission in 2014 from the literature. It appeared after perihelion in 2013, so the hypothesis that this was due to sublimation could be the triggering activity. However, since it's a fast rotator, it has a period of 3.33 hours, close to the critical speed for breakup. And since it has a high perihelia and low eccentricity, which means less solar heating reaches the surface, and so less solar heating reaches the surface compared to other active asteroids that show activity, then probably due to all this, the activity was due to fast rotation. There are no published studies regarding its activity during the perihelion in 2018, and so we observed it in 2014 to see if it reactivated or not. We monitored the object for different months before perihelion with the Asiago telescope in Italy, and after perihelion with the Very Large Telescope in Chile. And we saw no tail, so no activity. It is not a main belt comet. Now let's look at the nucleus characteristics and rotational properties of these objects. For 324p, I used the images when it was inactive in 2013. I normalized the absolute magnitudes to unit heliocentric, geocentric distances, and fitted the HG fixed function, assuming a C-type object. And I obtained the absolute magnitude of 18.4, consistent with the literature. And by assuming a spherical shape and an albedo used from the literature for this object, but usually used for main belt comets, I obtained a radius of 0.5 kilometers. We wanted to observe it when it was inactive in 2022 to study its rotational period. However, the Gemini North telescope had some technical issues with its primary mirror. So when it went back to observe, 324p was not visible anymore. And so we had to change target. And that's why we observed LH15 in 2023. And this was positive because we got some information on its nucleus. Since it was inactive, I did the same analysis I did for 324p. So I got the absolute magnitude and a nucleus radius of 0.5 kilometers, assuming a C-type object. And we wanted to analyze its rotational properties. However, the light curve was not that clear, as you can see. So we could just conclude there is no evidence of a period shorter than 2 hours. For 62412, since in 2023 and 2025, 2024 and 2025, sorry, it was inactive. So I did the same analysis. I obtained an absolute magnitude of 13.7 and a nucleus radius of 4 kilometers. It is much larger than the other two main belt comets. It is indeed the second largest active asteroid known after Shelia. And all these assuming a C-type object and an albedo from the literature. From the literature, we also know that it has a period of 3.33 hours. So from my Asiago and VLT data, we were able to confirm this rotational period. And from the VLT data that was obtained both in B and I band, we could also get the color index B minus I, which is consistent with a C-type object. So for this object, not only we could confirm no reactivation period, but also its classification. So to summarize, for 324P and LH15, we see recurrent activity near perihelion and for different perihelia, and this is consistent with sublimation-driven activity. They have a small nuclei, 0.5 kilometers, which is consistent with other main belt comets. And for 62412 instead, we had dust emission only in 2014, no reactivation in 2024. So no reactivation favors a disrupted asteroid interpretation. And since it also considering it is a fast rotator with a period of 3.33 hours, and its nucleus is much larger than main belt comets. Other examples of active asteroids are, for example, 133P Pizarro, which is the first main belt comet discovered in 1996. 238P Reed and 358P Pan-STARRS, which were observed in the recent years with the James Webb Telescope, and it detected water vapor. So this was the first direct evidence of water ice in main belt comets. Usually, we do not have spectra for this object, and so the evidence of sublimation is only visible if we monitor the object for different years and see its activity over time, especially near perihelion. And for examples of disrupted asteroids, we have Shelia and Linear, which showed dust emission due to an impact or collision, and 311P Pan-STARRS, which show activity due to rotational instability. This dust emission was very different than this dust emission because we could see 9 different tails over different months, and they were not, the object was not at perihelion, so sublimation activity was ruled out. And so the activity and the different dust emission over these many months cannot be possible with an impact, because considering the asteroid is fast, probably the dust emission was due to material sliding on the surface or being ejected because of this rotational instability. And I conclude with my publication from my PhD thesis. One was on 324P. It was the first long temporal evolution study on this main belt comet. And so it was a valuable contribution considering the long-term evolution of main belt comets. And for LH15, we published a research note, since before this paper, we only had one literature from only its discovery. This paper was gave some baseline for studying the object in details for the future and its future activity. Thank you. And if you want, you can ask questions in Portuguese. I should be able to understand.
Obrigada, Maria. Abrir para as perguntas. Professor Alto.
That example of asteroid disruption, that it released material only, no, the previous one, only for the perihelion of 2014. And but my question is dynamically, what could explain only at that moment and why at perihelion would be due to the tidal effect of the sun, or what could help to explain occurring just at that moment?
Yes, so this activity happened around 1 year after perihelion, so it's a bit difficult to explain it considering sublimation because of the time needed for the thermal wave to reach the subsurface ice. However, in some cases it can happen, so it was not ruled out. But we also do not see coma, so it's possible. It was not sublimation. Probably it's due to fast rotation, so the ejection of dust due to the rotational instability. However, we are still working on this. My supervisor, PhD supervisor, wanted to do a more detailed analysis from these specific images, but they were not available from the literature, so she's still trying to check if she can get them from the Magellan telescope. So it's still ongoing, let's say like this.
Mais perguntas?
By the shape or morphology of the tail, is it possible to distinguish between a sublimation event or disruption or impact or something? Or there's no resolution for that?
For example, for this case, the tail is very wide, or if it's an impact, it can create more than one tail. So that's why it is more easy to differentiate with sublimation. So in that case, probably it was an impact, but without having proof of gas detection, it is difficult.
And just another question, in your slide 9, I guess you have the magnitude changing over time. Yes, so it's a sharp decrease in just a few years, so you have a really short window to observe this kind of event, right? So it's likely we can lost a lot of this kind of stuff, because if you're not looking at the correct time, it just may be too faint to observe, right?
Yes, probably from 2010, it lost a lot of material, and then here maybe there was mantlings or reaccumulation of dust, but it is quite normal to see a decrease of activity over time.
Thank you.
Tem uma pergunta online? Não consigo ler, será? Ok. Eu acho que a professora Silvia quer fazer uma pergunta. Professora, fique à vontade.
É só perguntar? Isso?
Sim, eu estou falando em português porque ela também fala e entende português, tá, gente? Então, fique à vontade.
Ok. Parabéns pela apresentação, obrigado pela apresentação. Eu não sei se eu perdi essa parte, mas é possível estimar ou ter uma ideia do tamanho da cratera que é aberta?
O tamanho de quê?
Da cratera,
Cratera.
Crater.
And we do not have very high resolution images of this object, so not see a crater or not on the surface, so it's a bit difficult, I guess. We can estimate the exact emission time of dust particles by using the Sinda and Synchron model. So basically reproduce the tail of the comet of the object and see the exact moment when they were ejected and the size of the particles. But about surface information, we do not have those information.
So it's not something you see, right? Yeah.
No.
Okay. Well, thank you very much.
Ejected. Yes, we did it for 3 to 4P, and we estimated the gas production rate. It was consistent with what they saw with the James Webb for 3 to 4P, no, for those other two comets I showed. And we can also estimate the velocity of the particle ejection by analyzing the tail morphology. And also from that, we can differentiate between impact and sublimation. For example, for these disrupted asteroids, for these disrupted asteroids, the ejecta velocity was very fast, consistent with an impact. And for example, for this other object instead, 311P, the velocity was slower, and it is consistent with the sliding of material from the surface or ejection due to fast rotation.
Temos mais uma pergunta. Okay, Professor Antônio, thanks for your quite interesting presentation. I am interested in the percentage of comets among the objects in the main belt. Is there information about it?
Information on the amount of objects?
Yeah, percentage of comets in the main belt.
Yeah, so from a research I did last year, there are around 20 main belt comets and maybe 10 disrupted asteroids, another 10 objects we do not know the activity. But every year, thanks to the active asteroids citizen science, there are always new main belt comets discovered because everyone can help identify tails or coma dust emission from images of objects in the main belt.
Thank you. Any other question? Okay, thank you very much for your talk.